Okay, so this is the introduction to powers and square roots. So what is a power? Power is a shortcut for showing the product. I'm just moving something over. For showing the product of a number multiplied by itself one or more times. In other words, it's the product of repeated factors, like 5 times 5 times 5 times 5. And that power would look like this, what you see here where my cursor is, and I'm going to get that so that you can see a laser pointer. So right here, where the laser pointer is, shows what a power looks like. It is shown as a base with an exponent. The base is the factor which is being repeated, in this case, the number 5. The exponent is the number of times the factor is repeated, in this case, 4 times. So why is this useful? Powers are used a lot of times to express very large numbers, like in astronomy, the distance of planets from each other, or in very, very tiny numbers, like if you're looking at the sizes of an atom or something like that. The one way that it's sort of commonly seen, although I don't know that people necessarily think of this as powers, but if you remember doing geometry, when you do the area, when you find the area of a square, it's length times width, and both those numbers are the same because all the sides of a square are the same. So that would be the same thing as a number squared. So therefore, the area of a square with the sides of 3, for instance, would be shown as 3 to the power of 2. With the volume of a cube is another area where it would be commonly seen, because the length times the width times the height equals the volume of a cube. All of those numbers are the same. So if the sides are 3, then a cube could be shown as 3 to the 3rd power. And the other reason it's important is because powers are going to appear on whatever high school equivalency test you take. And they do come up a lot as you move forward through algebra. So I found this little scenario on Jeff Jacobson's Anywhere Math website, which is a website I recommend. He's pretty good about explaining things. But his little scenario was to show the use of powers. You have 3 friends. Each friend has 3 bags. Each bag holds 3 shirts, and each shirt has 3 buttons. Since each of the 3 friends holds 3 bags, there must be 9 bags, because 3 times 3. Each of the 9 bags holds 3 shirts, so there must be 27 shirts, 9 times 3. Each shirt has 3 buttons, so there are 81 buttons, 27 times 3. Another way of writing this would be 3 times 3 times 3 times 3. Another way of writing it is much simpler, 3 to the 4th power. So this is 3. All of these 3s are multiplied by themselves. So when you're reading powers, you would read 4 to the power of 5 as either 4 to the 5th power or just 4 to the 5th. 7 to the 6th would be 7 to the 6th power or 7 to the 6th. And this would be 10 to the 1st power or 10 to the 1st. When you're reading powers with exponents of 2 or 3, we often read them in a different way. Powers with an exponent of 2 and 3 of 2 is typically read as the base squared. So 5 to the 2nd power would usually be read as 5 squared. This is because, like I said before, the area of a square is the product of 2 equal sides. When the exponent is 3, the power may be read as the base cubed. So 5 to the 3rd power is usually read as 5 cubed. And again, this is because the volume of a cube is the product of 3 sides. Evaluating a power. When you're evaluating a power, that means you're finding its value. Since a power is simply a shorthand way of showing the number of times the base should be multiplied by itself, it is possible to find the value of the power by performing the multiplication. So the first thing you do is you turn the power back into a product. 7 to the third power equals 7 times 7 times 7. Then you simply do the multiplication. 7 times 7 equals 49. 49 times 7 equals 343. Therefore, the value of 7 to the third is 343. Some other examples. 2 to the 8th power is all these 2's multiplied by each other. So you can see why 2 to the 8th power is an easier way of showing it. And that equals 256 when you do all the math. 6 to the third power, again, 6 times 6 times 6 is 216. You can have a negative base, negative 6 to the third power, and that is going to be negative 6 times negative 6 times negative 6, which comes out to negative 216. And as you can see, the negative power came out, the negative base yielded a negative answer, whereas the positive base in this case yielded a positive answer. 4 to the fourth equals 256. Negative 4 to the fourth actually equals the same thing, positive 256. You can have fractions be raised to a certain power. Here, the fraction 1/3 is raised to the third power. You multiply 1/3 by itself 3 times and get 1/27. You can have the numerator and the denominator have different powers. So when that's the case, you calculate each one separately. 2 times 2 is 2 to the second power. 3 times 3 times 3 is 3 to the third power, which equals 4/27. Now, in the previous slide, it showed that a negative base raised to a positive exponent may have a value that is either a negative number or a positive number. For instance, negative 3 to the second power is, or negative 3 squared, is negative 3 times negative 3, which equals positive 9. Whereas negative 3 to the third power, or negative 3 cubed, is negative 3 times negative 3 times negative 3, which equals negative 27. So the rule for this is when the base is negative, if the exponent is an odd number, like 3, 5, 7, the value of the power will also be negative. If the exponent is an even number, 2, 4, 6, then the value of the power will be positive. A power can also have a negative exponent. For instance, 3 to the negative 5th or 6 to the negative 9th. A negative exponent is the reciprocal of a positive exponent. Instead of telling you how many times to multiply the base, a negative exponent tells you how many times to divide it. So when you're evaluating powers with negative exponents or finding their value, it's a fairly simple little formula that you go through. You simply make the base, the denominator, and a fraction with a numerator of 1. And then you change the exponent to positive. So 3 to the negative 5th equals 1/3 to the 5th. And it can be read as 3 to the negative 5th equals 1/3 to the 5th power. 6 to the negative 9th equals 1/6 to the 9th. And then once you have that, then you can calculate the value the same way you did with any positive exponent. So here's the first little rule for exponents. Whenever the base is 1, the number 1, raised to any exponent, the answer, the value of that power is always going to be 1, and you can see why. 1 to the third, 1 times 1 times 1 equals 1, because 1 times 1 equals 1, no matter how many times you do it. Rule number 2, any number raised to the power of 1 is that number. So 5 to the power of 1 equals 5, 6 to the power of 1 is 6, 7 to the power of 1 is 7. Again, it makes sense because you are using just one factor of the number. Rule number 3, any number raised to the power of 0 equals 1. That's a rule that is a little bit trickier, and it's just, I don't think it comes up on the exams. I just wanted to throw it in because it's a fairly basic rule that you might as well know. And then rule number 4, this is a pretty useful one. When the base is 10 and it's raised to a power, the calculation of the product is very easy. Whatever number the exponent is tells you how many zeros should follow the 1 in your answer. So here are some examples. 10 to the first power is a 1 with 1 0, or 10, which makes sense again because any number raised to the first power is that number. 10 to the second power is a 1 with 2 zeros, or 100. 10 to the third power, a 1 with 3 zeros, or 1,000, and so on. So you'll get mathematical expressions using powers. When a mathematical expression uses a power, the first thing you need to do is evaluate the power. So for example, 4 to the second power plus 7. First you evaluate the power. 4 to the second power is 16. Then you substitute that value into the problem. So you substitute 16 where the 4 to the second power is in the problem. You get 16 plus 7, and then you solve the problem. 16 plus 7 equals 23. A couple other examples. 4 to the second power plus 9 minus 12. First, you figure out 4 to the second power is 16. You substitute it into the problem. You perform the math. The answer is 13. Here again, even though the 8 to the second power is the second number, you still do that power first. You evaluate the power first. So 8 to the second power is 64. Substitute it in. 7 plus 64 minus 32 equals 39. A couple more using multiplication and division. It's exactly the same in this case. 8 to the third power times 9. Evaluate 8 to the third is 512, and you get 512 times 9. It's 4,608. 64 divided by 2 to the third. 2 to the third equals 8, so it's 64 divided by 8, which equals 8. So evaluating expressions with multiple powers is done exactly the same way. You simply calculate all the powers, substitute them in, and perform the function. I gave you a couple examples, which I think you can see where there are 2 powers. I evaluated the powers, substituted them in, and found the answer. Same thing here. Evaluated the powers, substituted them in, and solved for the answer. Now, sometimes there's a neat little trick when you have multiplication or division of powers when they have the same base. When you're multiplying powers with the same base, you simply add the exponents. So an example would be 3 to the second power times 3 to the 6th equals 3 to the 8th. I added 2 plus 6 equals 8. To see why this works, you can write the powers out as products. So the equation 3 squared times 3 to the 6th can be written out as 3 times 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 3. You don't need the parentheses because it's all multiplication. So it's all these 3's, which is the same as 3 to the 8th. So 3 squared times 3 to the 6th equals 3 to the 2 plus 6, which equals 3 to the 8th. So that's a very neat way of doing that without having to do all the writing it out and figuring. With division, it's the same thing, except that instead of adding the exponents, you subtract the exponents. So in this case, 3 to the 6th divided by 3 to the 4th can be spelled out as 3 factored 6 times in the numerator, 3 factored 4 times in the denominator. You can cancel out the 4 3's in the top and bottom. You're left with 3 times 3, or 3 squared. 3 squared is the same as 3 to the 6th minus 4. So You just subtract the exponents when you're doing division. So that's a very neat trick. Both of those can only be done when the base is the same. Okay, so now I want to talk a little bit about square roots. If the value of 8 squared is 64, 8 is called the square root of 64. This comes, again, from that square that I was talking about earlier. If a square has an area of 64, its sides must each have the value of 8. A square root is indicated by this symbol here. So when you see that symbol, and a lot of times it has a line that goes all the way over the number. When you see this symbol, it means the square root of 64. This means the square root of 100. This is the square root of 25. A perfect square is the square of a whole number. The square root of 100 is 10 because 10 squared equals 100. The square root of 100 is also negative 10 because negative 10 squared is 100. The square root of 25 is 5 because 5 squared is 25. It's also negative 5 because negative squared is 25. If you remember, negative times a negative is a positive. As you can see, each perfect square has both a positive and a negative root. It's helpful to memorize the common perfect squares. It'll save you a lot of time in the test, and they will come up often. And here's a little chart showing 1 through 15 squared and the answers. And then the reverse is the square root is plus or minus the square. So these are ones that are very helpful to know right off the top of your head. So there are a lot of perfect squares, but there are many, many non-perfect squares. If a number is not the product of two of the same factors, it is not a perfect square. For instance, 20 is not a perfect square because no whole number squared equals 20. 4 squared equals 16. 5 squared equals 25. There's no number in between there that can be squared to equal 20. Sometimes you need to calculate the approximate square root of a number that is not a perfect square. There are 3 steps to finding the approximate square root. In the next few slides, I'm going to show you how to find the approximate square root of the number 20. The first step is to find the closest root for the number 20. And you do that by checking square roots, and hopefully you can come up with some easily that will be close because you'll have certain ones memorized. But we know that 4 squared equals 16 and 5 squared equals 25. So either one of those is going to be your candidate for the closest root. 16 is closer to 20 than 25 is, so 4 would be the closest root for the number 20. The next step is to divide the original number 20 by that closest square root, by that closest root, which was 4. So 20 divided by 4 equals 5. For step 3, you take the average of the closest root, which was 4, as you remember, and the answer in step 2, which was 5. So to take the average, you add the 2 numbers, 4 plus 5 equals 9, and then you divide by 2, since we're taking the average of 2 numbers, and you get 4.5. Therefore, the approximate square root of 20 is 4.5, which makes pretty good sense because the square root of 4 is 16, the square root of 5 is 25, so 20 is going to be somewhere in between, and 4.5 is right in between the numbers 4 and 5. Another example, just to sort of show it all on one page, is finding the approximate square root of the number 32. The closest root is 6 because 6 squared equals 36. So then we take 32 divided by 6, the closest root, and that equals 5.3, which I rounded off. Then you need to take the average of 6 and 5.3. So 6 plus 5.3 equals 11.3. And to take the average, you say 11.3 divided by 2 is 5.7. Again, it's rounded off. So 5.7 is the approximate square root of 32. And that is the end of this video. I just wanted to mention Jeff Jacobson's Anywhere Math, which can be found on YouTube, and it supplied the shirts and buttons example that I gave near the beginning of this. So thank you very much, and that is it.
All right, wonderful.